Yes, so hello everyone. Welcome to BİLGİmusic seminar series, and this is the fourth seminar of this year. We have 6 more seminars coming up, and these events take place each week on Fridays this time, covering wherever you are on the globe. And it covers a wide spectrum of topics, and you can get information both from our website and our Facebook page about these events. And before I introduce today's event, I would like to notify you that this event is being recorded and that if you have any questions, feel free to type it into the chat box. I'll try my best to ask them for you. And of course, you can always turn on your camera and speak to ask questions at the end of the event, as we will be having a Q&A session. And today, we're very happy to be having Serkan Sevilgen with us. Serkan is a genius programmer, and he's a composer who uses a wide variety of programming languages like databases, cloud platforms, Linux operating systems, some music-specific ones including C-Sound, Super Collider, and MaxMSP. And his works cover, wide, let's call it oeuvre, so to speak, moving within the algorithmic composition, sonification, networked systems, soundscape music, as well as mixed music. He's also a tinkerer, creating his own sounding systems and various instruments. And today he will be talking with us about stochastic processes in music. And yeah, without further ado, Serkan, we're very happy to have you here and sharing with us, so welcome.
Yeah, thank you. And I want to thank you for your very nice words, but I think you raised the expectations to very high. I hope I can keep up with this. And I want to thank you to Bilgi Music Seminars that you are invited me to this such a special event. And it's such an honor and pleasure for me to be here. And I would also like to thank everyone who's participating today. And okay, then I'm starting with my slides. Okay, then our
Serkan, we
topic.
see, sorry, we don't see your slide. We see Spotify
Okay,
and code behind it.
thank you. And
Oh,
whenever
yeah,
you
here.
you get some weird stuff in the audio screen, please let me know.
Okay, yes. We
Okay,
see the slide.
we're going to talk about stochastic process in music, and it might seem a little weird concept and kind of esoteric concept. Stochastic, it really sounds nerdy or cool, but we can see later that it's really related to our world and how our lives really is working, and it's really relatable to uh, music. So I have a little problem here. Okay, my Bluetooth keyboard is not working, I guess. Uh, Sorry about that.
No problem.
Let me find. Uh, where's my presentation app? Okay. Well, and at the end, I will try to make a live demo, so it's not a really good sign for now. Okay. Let me stop sharing, and while I'm doing, why you are not working? Okay, it's really weird, but no worries. Uh, okay, so it's a issue with my Bluetooth keyboard. I'm
Okay.
going back to slide again.
Mm-hmm.
Okay, still sorry about that.
No
I
problem.
think it's now working, right?
Yes, wonderful.
Okay,
We see.
great. So, as Fulya mentioned, I'm an Istanbul-based computer programmer and composer. I did my BA in music technology in the previous millennium, or almost. And I started learning programming languages and starting to writing software for music initially. Then I see that it's a really good venture. So I kept up with the programming and pursued a career based on this. And then, better late than never, I start my master's in Miam and also in Yıldız Technical University. So I'm hoping to graduate this June. And I am a director of engineering at Tumblr. It's a Silicon Valley company develops data models for natural hazard risk assessment. So this is shortly my background. And yeah, what does stochastic mean? Stochastic is basically means random. So yeah, stochastic sounds much cooler, but we will be using the term random throughout this presentation. And the randomness is achieved by use of probability theory. A stochastic process is a system to create a sequence of symbols according to certain probabilities. So we're gonna see what this sentence really means. And if we have to explain what the probability is how likely an event is to occur. So I want to start with this. At my work, I have created a stochastic event set for earthquakes for 50,000 years. And, and I'm going to explain why it is 50,000 years, why it's not much shorter term. I had to make it 50,000 years or more. I'll explain later. And this is the map for only 50 years of our predictions based on our model. So as you can see, this map of Earth and all the red dots are earthquakes that we are forecasting to occur in the next 50 years. So why we are seeing the 50 years of this map? Because now we are seeing the USGS data for the past 50 years. Those are the observed events. So as you can see, the both maps are very similar, but not same. So this way we can prove that our model is performing well when we compare it to the real world data. So this is USGS observed data, and this is our stochastic event set. And why do we need a stochastic event set? So we are working with reinsurance companies and ILS companies, and ILS means insurance-linked bonds, and reinsurer means the companies who insure the insurers. So they are at the very top of this game, and there's a multi-billion-dollar industry, and they have to make some decisions and they have to clarify what are the risks they are taking. So we are providing this our event set for 50,000 years, and they are licensing it. They are paying money for it for us, and then they are using this model to make their own assumptions about their risks, and they are gonna lose or gain millions of dollars based off this model. So I want to start with this to show that stochastic is, as a term, is not some weird concept that Xenakis invented or something that computer guys or computer music composers like to use in their codes because they are lazy, so they can give some decisions to their code in as a random choices. But this is something really um, this is something that has parallels to our daily lives. Okay, so Yanis Xenakis, as you may already have known about him, he's a very prolific composer, and he's kind of grandfather or founding father of algorithmic music. And in his phenomenal book, Formalized Music, he defines two types of stochastic processes, and free and Markovian, and he calls free stochastic music and Markovian stochastic music in the book. So the free stochastic process means that each state is independent of the others, like a coin toss. We know that when we toss a coin, it can be head or tail, but whenever we repeat this, when we get the new event, we have to know that it doesn't relate to the previous event. But in Markovian case, each state is dependent on the previous state, and we're going to see some examples from the Xenakis and his music, and we're going to see how he is explaining his magic in his book later. So let's try to understand what is probability, what is randomness, because they are the key features of this process, and this talk is really about randomness. Okay, let's see the COVID-19 cases. So we know that 95 million cases around the globe, but these numbers are probably now much higher. They might be a little outdated. And we have 2 million of casualties based on that. So you may already know that there is a really little probability of dying because of the COVID-19. It's only 2%. But the catch is, the probability is 2%, but you're not gonna be 2% dead and 98% alive. You're gonna be either dead or you're gonna be either alive. And 2 million people is dead. So there is some misunderstanding with the probability. When a doctor says this operation has a chance of, let's say, 95% of success, it means that every out of 100 patients, he loses 5 of them. So we have to understand really what the probability means in this context. So when we get to the very easy example, we will toss a coin, and we know that if there's no cheating, the heads and tails probabilities are same. So there are 2 possible events, heads or tails, and each of them has the 50% probability. Actually, it's not for the probability in the mathematical sense, and I'm not a mathematician and I'm no expert in mathematics, I have to clarify this. But when we're talking about probabilities, we usually our maximum probability is 1. So the 0.5 is the probability for each event, heads or tails. So where we start to toss the coin, what do we expect? Yeah, we can have tails, heads, tails, heads, heads, heads, tails, tails, heads, heads, something like that. So as you can see, we have 10 events, and we will assume that we will have 5 heads and 5 tails, but it's not. Because the probability calculations are based on long-term observations. So we have to keep tossing coins for several thousand times. So then we will end up really 50% of likelihood. So if we get back to my stochastic event set for thunder, for earthquakes, I had to create this event state for 50,000 years because it has to be a very long term to make sure that our calculations is really correct. So this is why we need to observe for a very long time to get this, let's say, probabilities really happens in the real life. So I want all of you to pick a random number from 1 to 5, several numbers. Just write it down or keep in your head. And Fulya, can you help me with this?
Yes, sure.
Yeah. Yeah, you didn't know that coming, but
Nope. Let's
can you
play.
just very, very quick, just random numbers between 1 and 5. Can you pick one? Come on. Yeah.
Me? Oh, two.
Yeah. There's
Yeah.
2. Another one.
4.
Another one.
1.
Another one.
3.
3. Another one.
5.
5. Okay.
Oh, I went through all of them without repetition. Okay.
Yes, this is what I was expecting from almost everyone. So I'm not sure if you really did this now with Fulya, but Fulya just said 2, 4, 1, 3, 5, and none of the numbers are repeating. And you worked really hard to find the one that you didn't say. Okay, this is something very important. This is something with our perception of the randomness. Actually, if we have 5 numbers, the probability of each event, let's say the numbers here, are equal. So when you pick a number from this set, it can be, yes, 2. But you can get another 2 because the 2 is already is there. We didn't erase this number. But when we say, come on, pick a number, pick a random number, we just tend to not repeat the numbers that we are picking. It's something important. Let's go with this. Okay, assume we have a 12 numbered balls in a bag, and we draw one random each time as we did with the 1 to 5 numbers, and we do not put the ball again in the bag. So without putting it back, so a possible result is 2, 1, 9, 10, 5, 3, 4, 12, 8, 7, 6, and 11. And it can be in any order. And as you can see, it's very similar to the number patterns that Fulya picked for us. So they are not repeating. And we get each number once. And this might reminds you something from music, from the early 20th century music. So we have 12 events, and they are not repeating. We don't repeat any number without just going through all the numbers we got. Okay, just keep in this mind. We get back to this again. Now we are doing the same experiment with a small change. Now we are drawing the same balls from the same bag, but we are putting the balls, we are putting the numbers that we are picking to the bag each time. So a possible result: 5, 4, 3, 2, 2, 2, 2, 2, 2, 9, 2, 3, 3. It's really possible. Maybe you don't pick this, you will not pick this numbers if you see it in a lottery ticket, because it feels really unlikely. But at each event, we have the same probability for each number. So let's say, I think you can see my mouse, right? Can you see my mouse? Okay.
Yes.
So this is our first event. And we have 12 events. So the any probability is 1 over 12. And as we said earlier, this is free stochastic processes. So each event is independent. So each of the events can be any of the 12 numbers. And we can also end up something like that. It's still possible with the replacement. But it's also possible to have some numbers repeated, or we can see some patterns here. I can see some descending pattern here. But this is me. I am seeing this pattern. It's actually a random process. So which one, yeah, do you think feels like random? This one feels more random, or this one feels more random, or this one feels like more predictable. So any Fulya?
Well, they both
Can you
can
say
be
about it? You're my
random.
volunteer today.
Okay, yes, they both could be random according to
Yes.
me. Yeah.
But when you
can't
look
choose.
at,
Maybe the
because you
repetition one.
pick this one.
Yeah, I mean, if I had to choose, I would go with the repeated one.
Yeah.
Yeah.
So when we get back to this first array of numbers, it is for me very similar to a 12-tone row. So we get numbers, they are not repeating. And if we are going to generate another set of random draws from this array, probably we're gonna create very similar to this, but still not repeating the numbers. So I'm speculating here. So, and I'm not saying it was Schoenberg's intention to create music out of random numbers, but this resembles very much what we consider as an random choices. So we can maybe talk about this later if you have any ideas about that. I'm not saying this is why serial music just get the very large audience, because it is very feels like random music is hard to get. I'm not saying that, but I'm just speculating about that. And Yes, when we toss a coin, we know that each event has the same probability. It's same with these numbers. They have the same probability. But if we think about the, let's say, a dice, which is cheated, that is built to return more 6 and less 1, then we can say that the probabilities of each event are not equal. So if we have each event has the same probabilities, we can say this is uniform distributed events. If the events have different probabilistic values, then we have other distributions here. So we're going to see Poisson next, and you might also remember Gauss from the student grades curves, you know, the bell curve. So it says that the not every student gets just random grades, but they get populated into some area around, let's say, 70. We have more 70s and 60s and 80s and less 20s. So distributions give us to make some predictions about the real world issues. Okay, when we get the Poisson distribution, and which the Xenakis used is extensively. It has many everyday uses in several industries like telecommunication, astronomy, chemistry, biology, management, finance, an earthquake. There's an earthquake. So, yeah, and that's right. I have used Poisson distribution to create my event set for work. And other use cases in several industries. So I have to just stress that stochastic processes, randomness, and those distributions that are used by composers are not really some weird, hard to understand, or trying to be pretentious or something. They are very related to our everyday lives, and this is why composers adapted them to create their music. So I'm coming to now Xenakis, and it's an example from the book, his formalized music book, Apocalypsis. And it's music for 21 instruments orchestra in 7 timbre groups. And this is the Poisson formula. This is used for calculating the probabilities. It might seem very cryptic, but it really is not, and we don't need to worry about too much mathematics here. Lambda is very important. It says where will be our main distribution will be. So if we say our lambda is 0.6, so it will be around, we will see the tip of the curve more around this number. And Xenakis calculated some events. So let me go to this. This is the matrix that he calculated. So it's actually, as you can see, this axis is time, this axis is the instruments. And he created 100 and 96 cell of matrix, and those are the empty cell means no events. This is a single event, this is double event, this is triple event, and this is quadruple event. So he wants to have no event to quadruple events, and he uses the Poisson formula to get the probability for each event. So for no event, so we are putting lambda here, which is lambda that Xenakis uses for this piece, 0.6, and this is the event number. So we don't need to worry about here because computers just do everything for us. So we can calculate here. The no events probability is 1.5. Single event is a little lower, and double event is getting much lower. Triple event lower, and quadruple event is then very low. So when we get to this matrix, we can see the quadruple event, which has the lowest probability, occurs only one time, because this probability is very low. And we can see the no event has the highest probability. We are seeing a lot of empty cells. So without going too much further, let's hear a little from this piece. So this is actually, we can see as a graphic score. But unfortunately, Xenakis explains about this piece, how he did manage to calculate those numbers, and then just stops somewhere without giving too much information. So we don't really know what does it mean about this no event, double event from his book, but we can speculate about this. And since we have the formula, and this is something that I did. I tried to recreate the same matrix. So this is the zero, no event, single event, double event, and we have triple events, and we have this quadruple event. Yeah, this is all exactly the same as this, but this is, let's say, digital. This is data. And then I have plotted this. This is the same matrix, but with nicer colors. No event. Let me explain you the color code here. This is no event, single event, double event. Greens are triple events. As you can see, we have only 4 triple event, and we have 1 quadruple event. And then this is the probability distribution, because our lambda is 0.6. We have more 0 events, and then it goes back to, as you can see, this is the quadruple event here. So this is our distribution based on Xenakis' piece. So Then, using the Poisson formula, I created with the same lambda, with the same number of cell number, and then I create the new matrix here. So, and I have plotted it. So you might see that it's similar to the previous one, but it's different. The order of the events are different, and we have 1, 2, 3, and 4, 5, 6 triple events here, and again only one quadruple events. So this means that if we run the same algorithm again and again, and if we're using probabilistic methods, stochastic processes, we're gonna have similar but different results each time. And we can even be brave and recompose the piece with this new matrix, or we can compose a piece based on this alternative occurrence matrix. So we have the similar distribution. So it shows that what we are doing is really similar to what Xenakis did in this music. And we're gonna getting very interesting topic. As I said earlier, there are two stochastic processes, free and Markovian stochastic processes. In Markovian stochastic process, each event is dependent of the previous events. So this is an example from my music again. Let's say we have this kind of sequence here, and then we can calculate the probability of if we are at the state of A, what's the probability of the being B or A for each state. So it's really a simple mathematics. From A to B, this transition happens 17 times, and let's say A to A happens 6 times. So it's total 23 times, and then we can calculate the probabilities for each transition. From A to B is 0.74, and A to A is 0.26. We can also calculate going from B to A, this transition from B to B, and pretty much the same. And we have this 0.63 and 0.37 probabilities. So as you can see, when we add them up, it will just 1. So it's a transition matrix which is calculated previously. So it means, how can we read this? Going from A to A, our probability is 0.26, and going from A to B is 0.74, and going from B to A we have probability of 0.63, and going from B to B is 0.37. So it's not 0.5, 0.5, 0.5, 0.5. So we can see that if we can use this transition matrix and create a new sequence, we're gonna see more A-B patterns than AA patterns, or we're gonna see more BA patterns than BB patterns. So let's hear an example piece that Xenakis used Markovian stochastic process to create. This is analogic A, B. The A part is for orchestra and B part is for electromagnetic tape. And it's based on granular synthesis, we can say today. As Xenakis put it as like grains of sounds. And he used some compositional method he calls screens. We're not gonna get too much into this. But he uses Markovian probabilities to determine the order of those screens, those building blocks of his composition. Let's hear it analogic now. I don't know if you can catch the patterns. I don't say I could do it, but maybe few people in the audience could do that. So those are the example of music by Xenakis. And I'm gonna play another piece and then explain what is really about. So any ideas? Which piece is this? Who might be the composer, or which era do you think? Any idea? Okay, it sounds like from the classical era, and it sounds like Mozart. But actually, it's composed by a American composer David Cope. So David Cope is very interesting person. After he struck by a composer's block, so he just wanted to analyze his own music and create music in style of himself. But to make sure the system is really working, he tested with other composers' pieces. So it's a piece by David Cope called Symphony After Mozart, and this is the Allegro part. So what he did is he took the sequence of Mozart music and analyzed with the Markovian stochastic processes, and he calculates all the probabilities of note events transitions, and then with the transition matrix he created, he composed this piece to prove that his system is working. And and in this, we are living in an artificial intelligence craze. So everyone tries to use AI or machine learning to create music. But until now, nothing can really pass the Markovian Markov chains and Markovian stochastic processes in this regard. Okay, so if there's a question I can take now, and I would like to use the remaining time for a live demo. Fully, I was saying that if there's a question, I can take now because I'm
Yes.
going to demo
Okay.
section.
Wonderful. So if anybody would like to write some questions in the chat box, or you can just directly turn on your camera and sound and ask directly if you have a comment or a question.
Okay, then I can proceed. So we're gonna first an excerpt from one of my acousmatic piece. You're gonna hear a very strong noise sound, and you're gonna hear the panning effect. And this panning effect is so I have employed some random choices in the code, and this um, panning will come from some random choices by the computer. So in electronic music, because we can use computer programming very easily, I prefer to use C Sound or Super Collider for this manner. If you use computer programming for to compose music, then you can easily add random generators easily into the mix, and you can give the ability to make some decisions to the computer and to the algorithm. So it gives you to ability to share the decision privilege between the computer and composer. So it might be a good thing, or it might be a personal preference, but it also gives us the ability to create generative music more easily, or if we really want to have some stochastic events, some random events that is really hard for a human to create by own hand, then computers really helps by doing so. And I hope you can hear me because it's a prayer time, and I have a very I have very nearby mosque.
We can hear you clearly.
Okay,
Yeah.
okay, then I will. Where is? Okay, here. Sorry about that. Now I am going back to my code, I think now you can see some colored text and score on the right side. So let's start with this. Okay, so it will be a live demo. I hope everything will go well and we don't have any problem, but it's always really fun to make those stuff in real time before the audience. So you don't have to worry about this part because there is some computer program that I have written is running in the background. It waits for the incoming OSC messages, and whenever it gets an OSC message, it will create a score using Lillipond as a backend. So this part is important for us. So I have an array of pitches. I have also included the rest for the sake of the simplicity. So we have rest C sharp D, and we are going to be its chromatic scale, and those are the registers. It's how Lillipond understands registers, so don't worry about that. But low and high, and those are the durations, those are the dynamics, and those are some expression marks. So I have a simple code here. So what it does, it will randomly chooses from this list for pitch, from this array for register, and from this array for duration, and it's going on. So it is going to be totally random. So the probability of likelihood of each music event is same. And now we are creating something for Lillipond, and we are sending our score to the score generator. So the only thing that I am actively changing and that I have the power on it is the length of the score. So I'm defining here how many note events I want in the score. So let's try this. Okay, I have 2 note events. Can you see that? Can you catch it? Yeah. Is it fun, right? So as you can see, we got a little weird, but because we are just randomly choosing without thinking about the compositional process, or if because we have rest in the pitches and we can have rest and we can have dynamics with the rest in this situation, but don't worry about that for that. So I have 2 note event as intended, and their durations and their pitch, their registers and their dynamics, and their everything has been chosen by this code. Now I'm gonna create a new one. Now I want, let's say, 4. Okay, we have 4 note events now. As you can see, I'm only changing the number of the note events I want, and I got these let's say short motifs. I can go on with this, let's say 10. Then we have another sequence of notes. So this is my example for random choice for each event has the same probability. And then I want to go to another code. It is very similar but not same. So I have a similar array, but then I just get the rest as standalone parameter. I have those registers, durations, dynamics, lot dynamics I got, and some expression marks. Then I have a function here that I defined the Poisson distribution, the Poisson formula that we have seen in the slides. This interesting with the lambdas and k and other stuff, and we don't have to worry about that because we have this in this code right now. We have this Poisson formula, and we have this function to create an pattern based on Poisson distribution. And I would like to have this example in, let's say, piano music. So I've chosen the piano. So if you are interested, this is for Lilliput. Lilliput is a text-based music notation program. You write like this, and when you generate it, you have a score as a PDF. So I really not I can't really use the graphical user interface programs like Sibelius, Finale, or even Ableton Live. So I have to use this kind of stuff, but it also helps me to easily combine my code to create a score. So I have generate one and generate two functions here. One is for left hand and one is for right hand. And I want to have, on the left hand, I want to have some chords, and on the right hand, I have some motifs. So let's get to this. So I'm using the same function Poisson for, and I'm changing the lambda parameter and the data set. I'm creating pitch, duration, dynamics, and I'm also including the rests, and I want to have longer rests, so I have some rest repeats here, and then it does some calculations and then creates it for us. Let's go back to the generate Poisson formula. The first one is data, as you can see here. This is my data. I want my pitch generated from the pitch array, and this lambda is important because you see we have 12 notes here, 12, let's say pitches here. Then I'm saying that I want, if it's 3, so I want more here. So I want more of those notes and less these notes. So I'm saying, let me, my lambda is 3, bring me more those notes. And it's same for others. Let's say I'm saying for durations, I say 2 as my lambda. So I want more shorter notes. I don't want too much larger notes, but I will have some them, but the probabilities will be very low. So let's run this code. Let's see what is happening. So it is, yeah, it's a new score right now. As you can see, I want my notes can be playable by a real pianist. So I want them aligned like that can be playable, and I don't want too much, let's say, jumps here. But what if I change this? Let's say in the right hand. This is my right hand. Right hand. Yes, this is my right hand. Let's say for durations, I want longer notes. Let's come to here. Durations 2, 3, 4. It starts with the 0 in computer language. 0, 1, 2, 3, 4, 5. Let's say this 5, and I'm only changing the duration here, and I'm applying this code. Okay, now I'm running it. Let's see what is going to happen. Okay, as you can see, I have much longer notes in the right hand. I still have shorter notes, but I have much more longer notes. You might say, hey, there has to be less shorter notes, but it could be if we say, so you see we are creating very small number of notes. So if we generate, let's say, hundreds or thousands of notes, then we can observe that the real data that we created will be very similar to the calculated probabilities. So I think this is the end of the presentation. So I'm glad everything went well with this live demo because it was really risky. So yes, thank you for listening. Thank you for attendance, and thank you for your attention.